All right, so up and running, capture the board. Yep, that's good. Yeah, we'll take care of all the markings and everything as soon as we're done. Just a little check, all right? I'm gonna give you back your test. Test comes back today. Shh. Don't tax the man, he's fasting. All right, so this worksheet is basically the same test you took. So what I'm hoping you'll do in a little while is get in groups of maybe 3, might be best, at least one partner. And I want you to go through your answer key when it comes back to you, and any problem you got wrong, if your group, somebody in the group knows how to do it, show them how to do it, and then try the one that's on the paper. Okay, and go through the entire test as much as possible and see if you can maybe correct. Now, some of you may have already done that, those of you who are responsible and took an answer key. Some folks, you were fasting though. That's right. Some folks didn't, because I've got a whole stack of these answer keys. And I made 30 and I got 31 students. Oh, anyway, so cubics, where are we at? Well, we started this whole discussion by drawing some cubes, tying it to the graph, looking at the rates of change. And it was actually totally dependent upon, where's my little manipulative here? Well, I guess one of them's here, right? Adding surface area to the cubic, length, width, and a little bit of thickness is volume. So we added a little bit of volume, but what size volume? Definitely linked to square area here. Okay, so that's what we were looking at. Cubic always increasing. I think we can see that. -8, -1 is bigger than -8, so on and so forth. And I hope you can see there's acceleration. 8 to 27 is 19 units of change. But tack on one more unit on the dimension of the cubic, you go 27 to 64, which is, oh, brain, come and help me. 37, I think, unit change. I could have botched that just then, but it's accelerated. The volume is accelerated. So end behavior versus local behavior is what we're trying to zoom in on. Trying to zoom in on that local behavior. Okay, then we switched gears and we said, well, what's the difference between x cubed and x times x minus 2 times x minus 10? They're both cubes, but very different drawings. All right, x cubed is simply x times x times x, and I'll refer to that as a perfect cube. All right, so where have we manipulated these kinds of problems before? With quadratics. X times x minus 10, rectangle. What do? We change it into a square. How do we do it? We work with the constant and we even it up. We divide it by 2 and even it up. Okay, and what are 0 and 10? The roots of the quadratic. All right, and if you got roots, symmetric roots, then you got a little feeling for what's in between for the mins and the maxes. All right, so it leads us somewhere. So, well, when I look at this, I go, well, what's a cube? It's a shape, right? Can we change this into a perfect cube? Well, what would you have to do? Oh, I'm looking at the wrong one. What would you have to do if this cube was going to get turned into a geometric shape where all 3 sides are equal? Well, I think you got to work with the surface area here, right? And how am I going to make all sides equal? This 0 root, 10 is a root, 2 is a root. The same thing over here, 0 and 10. Those are the roots. What do? We add them up and divide by 2. And that gives us, x minus 5 times x minus 5. And I just thought I'd throw a 5 minus 5 in here just so you could see what the squared term is, what the linear term is, and how does the linear terms compare to the squared term? Twice the size and opposite. And hasn't that been showing up in all of our putting quadratics into graphing form? Okay. So what, again, is the purpose of all this? Well, let's take this particular cube, and I multiplied it out. Ax cubed plus bx squared plus cx, and the d term is 0. Okay, and the d term is a constant, and this one, the constant is 0. So really, this has 4 graphs, potentially 4 graphs coming your way. I've eliminated the constant. We'll see why in a second. All right. And so here's the picture. I've got 20x, which is green, minus 12x squared and x cubed. And the question is, can your brain put those three things together? It can, but it gets harder every time you throw another term in there, right? An x to the fourth, an x to the third, an x squared, and it gets complicated. So what do we try to do? We try to rewrite it so we can see it, all right? And there's something very interesting in this whole process. For instance, if I multiply x minus 4 cubed out, right? Because 0, 2, and 10 are the roots, and the average of the roots is 4. So I should be able to reshape this thing into x minus 4 times x minus 4 times x minus 4. Okay? And if I did that and I cubed it, I actually did it somewhere. I thought, oh, I did it here, I guess. I did x minus 4 squared, which is x squared minus 8x plus 16. And then I multiplied that by, I did this wrong, by the way. Did it too quickly, right? So I would do that times x. And, oh, I needed to, I did it. Anyway, you're going to get the first two terms, which I want to talk about more about tomorrow. All right, so writing x minus 4 cubed actually eliminates the squared term from our visualization of what's going on. So I can rewrite that calculation that way. And that only has three terms. It's got a constant now. The constant's minus 48. And I did this with the last class, so I'll get rid of this. See if I can get, I don't know what color this is, but whatever it is, it's going to have to do. Okay. So there's your linear term. There's your minus 28 going through 40. Hope you can see that. So there's your linear term. All right, somebody asked me a question. So I've written this as actually as two terms. Right? There's your linear, there's your cubic. And now I'm not at 40 because when I add all the y values, I'm really at negative 48. Right? Remember we talked about constants simply move graphs north and south. Okay, so that's really just two graphs. So what's this going to look like if you added those two graphs together? Well, this is pulling down. This is pulling up, but at different rates, very different rates. So for instance, if I put a 5 in here, 5 minus 4, this has gone down 28 units. Put a 5 in here, I'm going up 1 from this height. So which way is the graph going to go? It's going to go down. And the question is, at what rate? Well, it turns out it's the rate of the linear function, because the rate of a perfect cube, we said, no volume, no surface area change, right? The bigger the volume, the bigger the surface area change with a little bit of thickness. Am I making some sense? So what I get is a graph that looks like this. Let's see. And that's negative, that's positive 4, comma, negative 48. And I'm moving down at minus 28 to 1 at that instant. I've got a little feel for the graph. Whereas everybody studies factors, but that's not really what's going on. What's going on is geometric, right? You've learned how to use factored for quadratics. How do you solve x squared plus 20x? Oh, x times x plus 20 equals 0, right? I mean, you've already done that work. Adding a dimension doesn't change an understanding of that process. You either have that in your pocket or you don't, right? And you just apply it to the cubic. It's one more step up, but it's no big difference. The real issue is what's creating this stuff. What's creating the fact that this x value now is 4 plus or minus the square root of negative 28 over, what was it, over 3 times a, so 3, right? So that's the x value of, oh, I'm sorry, positive 28. Got to change the sign. So that x value exists, and you'd have to put that into the calculator or the function to find the y that goes with it. But there's things that you can do quickly and easily with a cubic if you understand the geometric ramifications of what you're looking at. Okay, so I hope that kind of summarizes a little bit what we're talking about. I want to take it further. All right, so that's that discussion. So I'm going to put an end to that one, kibosh.